ARMv9 is here, and although it took nearly 10 years to arrive, it comes right at a major inflection point in the semiconductor industry where all of the major chip makers have started dabbling in processor architectures outside of their own heritage. The roadmap decisions of today, such as the massive emphasis on AI and ML workload processing in ARMv9, will have significant ramifications for the embedded systems of tomorrow. And oh yeah, what does NVIDIA's potential stewardship of ARM mean for competitors who also happen to be ARM licensees? Brendan and Rich discuss. Later, Intel's Sailesh Kottapalli, Senior Architecture Fellow, and Mandy Mock, VP and GM of Product Engineering Systems, join the insiders to dig deeper into Moore's Law. Could the price, performance, and size of current and soon-to-be developed processors take a hit if they're unable to keep up? Finally, in this week's Tech Market Madness, Perry Cohen tries to make sense of the edge with Matt Trifiro of Vapor.io and Jacob Smith of Equinix, who co-chaired the LF Edge's 2021 State of the Edge report. All of these years later, will we finally have an answer to the question, what is the edge in IoT? And if we can agree on something, how will it reach critical mass? Here's a hint: open source.
Hello and welcome to the Embedded Insiders. I'm Brandon Lewis, Editor-in-Chief of Embedded Computing Design. I'm here with Rich Nass, who is a pro. You just told me you can talk about anything in the embedded space.
What's that phrase? Inch deep, mile wide.
Right? Yes, jack of all trades, master of none.
Hey, I can master a few. I can definitely master a few. If you check out my smart home, you'd say, "Wow, that is so impressive."
Oh, we never actually talked about whether or not your internet ever came back on.
Well, we wouldn't be here if it didn't. So yes, it did come back on, and we are alive and kicking. I was actually gone for a week, and it's very comforting to know you can monitor the entire house from wherever you are, just by your phone. And it's definitely great at parties when you can show people what you can do from afar.
You know, one of the things that's kind of funny about this, I was listening to this comedian the other day, and he was talking about how being connected and having so much information about everybody's homes on the internet is like, oh, you should show up at a party and you're like, I don't need to know where the bathroom is, I already do. But anyway, there's a ton of big news this week. Or actually last week, because we're speaking in the future. Last week,
so that means the Mets are officially in first place already, right?
The Mets are in first place. The Lakers have been bounced from the NBA playoffs. But ARM released ARMv9, and it's been about 10 years in the making, but obviously this is big news for...
Is it really 10 years?
It's been 10 years. I was going to say time flies, because I thought that we were talking about V8.
You were in like third grade when the last version came out. Wow, that's incredible.
Yeah, it has been 10 years. And, it's not as big of an update as you got when you went from V7 to V8. There was all the 64-bit stuff when you went from V7 to V8. There was a bunch of additional instructions. This isn't as big of a lift as that was, but it's still fairly significant. And a lot of the upgrades that they've added in V9, there are some extensions, but mostly we're talking about enhanced DSP performance and vector processing capabilities, more around security, and then a big time focus around AI and machine learning workloads.
So the first thing that jumps into my head is how much influence did NVIDIA have? And I'll probably say almost none from a inside level, but at the top level, when you just said, there's a focus on AI, that just screams out NVIDIA to me.
Yeah, I would agree with you. I think that this has been in the works. ARMv9's been in the works for so long. They started working on V9 probably as soon as they launched V8,
or before.
Yeah, or even before. So I don't think NVIDIA really had anything to do with most of the upgrades you'll see here. Of course, ARM does work closely with partners and its major partners. So their requirements are, of course, integrated into the roadmap. So there may be a little bit of NVIDIA here or there. There's double-digit performance increases expected via ARM v9 and over 30% they're claiming over the next 2 generations of chips, which is starting to lean, more and more towards what you would see on an NVIDIA announcement. There's not as much here about the low power in the headlines. Of course, there are efficiencies to be gained, and I do think that a lot of what V9 is trying to accomplish is being able to do some of those machine learning workloads, AI workloads, not only on Mali GPUs and some of the neural network processors, but keeping them in the CPU domain, which is really important when you start talking about the combination of NVIDIA and ARM, because you're going to have the ability to offload certain workloads that are AI from these huge GPUs of NVIDIA onto something that's really efficient, like an ARM CPU. So a lot of the upgrades are certainly complementary to what NVIDIA is trying to accomplish.
Are you saying it's separate pieces of silicon, or within the same die when you're offloading?
I'm saying that within the same die, the different IP blocks that are within the same die. So yeah, I think when I was talking about ARM's other offerings, this NPU block, the neural processor block, and then the Mali GPU block, how all of this stuff works out with NVIDIA. They've been integrating ARM cores into their processors for a while, but on the same die, which actually I brought up in this chat that the media had with some of the technical luminaries over there at ARM, was, what does all this mean from a memory standpoint? And I don't mean off chip. Obviously, when you go off chip, you're consuming tons of power, and you open up whole big cans of worms, especially in embedded use cases. But on chip, there's so much data that these types of applications are going to be sucking in. Are AMBA buses going to be sufficient anymore? How are we going to need an evolution there? And really what the upshot was changing the way that memory architectures work altogether. So maybe we start using 3D memory, and that gives you more area when you're passing data. So a ton of really intriguing developments are on the horizon. Stay tuned.
Yeah, if you're bringing imaging into that equation, I don't even know if what you're suggesting is possible because of the amount of data that would have to come through. The memory structure, the way it is, just making tweaks to that memory, you'd probably need an overhaul to do AI with a vision system. I just don't see that that's possible to do with existing architectures on chip.
Yeah, to your point, you're going to need so much memory. Yeah, at that point, how big is the chip? Our embedded chips are going to be the size of the NVIDIA chips, right? In order to do that. But I think that was sort of the point about using these 3D memory architectures, is that, instead of going out and out and out, we're just going to start going up, and maybe we'll be able to get sufficient amounts of memory for certain use cases. It'd probably be a really low end vision use case. You're not talking about like constant, video surveillance, object detection and stuff. But, maybe for some reasonable, I don't know, it depends on who's listening, what reasonable is, but you may be able to get enough on there.
I think I just came up with the solution, but you have to promise not to tell anybody.
Lips are sealed.
We need to redefine the edge. So we're actually pulling back the edge somewhat. So the edge isn't really the edge anymore. It's more of a gateway where you're doing what we just described at that gateway, and you're using the less memory intensive at what is now the edge. So you're adding in a layer there.
A while ago, we had Stacy Higginbotham on, and she was like, "Oh, why would NVIDIA care about all these tiny little Cortex M's?" Well, this is exactly why. I remember we were talking about, if you have a Ferrari, why would you want a bicycle? Well, if you got enough bicycles, it's significant. The one caveat in that is Intel, NVIDIA, all of these all of these chip vendors who've been working in the data center, for lack of a better term, have seemed to have wanted to create more and more monolithic platforms and push them further and further down. Obviously, they can't go all the way down to the very, very far edge. But, does NVIDIA want to draw a line in the sand? Is Jetson as low as they go? Do they say beyond that, we're just going to let ARM do all of this stuff? And if ARM cores are doing all of that, what are you talking about in terms of the capabilities that are needed to do AI at that edge? Because you're now talking about a class of processor that's resource constrained. To your point earlier, if you're trying to do imaging stuff, you can't really do it unless you've got gateway class resources.
But you're making the assumption that there's a line in the sand between NVIDIA and ARM. And 3 years from now, that line probably won't even exist.
Hello and welcome to the Embedded Insiders. I'm Brandon Lewis, Editor-in-Chief of Embedded Computing Design, and we're back with smart home aficionado Rich Nass. How you doing, Rich?
I am doing great. Even we had a conversation last time, and we sort of got cut off because we don't want to make these things too long. But we were talking about if you had, see if I get this right, if you had a fairly large processor, but if you just needed to do some single function thing, is an ARM core the right way to do that? And what I was going to suggest at that time was maybe that's actually where RISC-V comes into play, where you put a single function RISC-V core into that same piece of silicon to do your single function, even if you're bringing in imaging data. For example, if you're doing a security application with imaging and you just want to know if something different has happened in that screen, if a cat walked by, your single function just cycling continuously, not using a lot of power, would be the right way to do that.
Yes, but are we still talking in the context of an ARM processor or just any processor? So this single function RISC-V core is integrated into any SoC, or is it an ARM-based SoC with a RISC-V core, or is it?
Well, I was actually thinking of integrating with the GPU, where once you see, the image changes, the flag goes up. Okay, we need to bring the GPU in to do some detailed analysis on that.
Mm-hmm. So then we're really talking about the world of everything, the way everything's been going, of these custom SoCs where you could be licensing this GPU core, maybe from ARM, maybe from one of the other Cadence type guys, some other core, and developing a really specialized chip for a really specialized use case.
Yeah, why did you leave out NVIDIA in that sentence?
Well, NVIDIA doesn't license NVIDIA GPU cores.
No, but they would license in somebody else's core into their GPU.
They would license,
bring the RISC-V core.
Right, they would bring a RISC-V core in. I was thinking it from the context, from the perspective of somebody who was trying to get a chip for a use case. I wasn't thinking of NVIDIA, making a general purpose chip, because NVIDIA is not going to make a very specific chip unless you've got a whole boatload of money.
So you don't think you'll have an NVIDIA chip in your smartwatch? Probably
not. That's a really big watch. It's like one of those Flava Flav like clocks around your neck. But that being said, all of this stuff, I think we've hinted at it a couple of times, all this stuff creates a really interesting market dynamic now. So I think you brought up at one point, where does NVIDIA buying ARM leave Xilinx, and where does it leave Intel? Where does it leave all these other massive, ARM licensees from the past? And I spoke with Xilinx a few weeks ago, and they said, they've re-upped their relationship with ARM for the next generation or so. Everything's subject to change, but they're going to continue on that path basically because they have to. They can't just pull the rug out from underneath their customers. It's also sort of interesting the fact that Xilinx was probably one of those those lead customers of ARM helping influence decisions on the roadmap. Intel may have been involved in that too. Those are big pockets in a pretty small room, helping guide ARM. And now NVIDIA comes in and sort of turns the table all the way around. Where does that leave these guys?
Well, it's certainly an opportunity for a RISC-V vendor to be sucked into a Xilinx core.
Mm-hmm.
I honestly don't know where it would leave a Xilinx who's still looking for ARM, asking NVIDIA, are you guys going to keep going down the path? Do I stay with you, or do I need to start looking at what my options are?
When I spoke to Simon Segars the other day, he was like, oh, well, anybody can continue licensing ARM who wants.
But licensing what 3 years from now? Who knows what it is that they'll be available to license? NVIDIA has sort of, I think, said that the only path they want to go down with ARM is AI.
Publicly, ARM is on the position that status quo will remain. There's business as usual. We're just going to continue doing our own thing. Of course, that we've heard that a bunch of times, right? Not only the fact that, oh, we're just going to continue doing what we've always done. Okay, well, we'll see what happens when NVIDIA course corrects or decides that, forget all of this R&D that you're doing into Cortex, into the embedded class. Actually, speaking of this, at the hypervisor layer and up now in ARM v9, they only support 64-bit, 64-bit hypervisors, 64-bit operating systems, and that's not a big shocker. But, there is this migration slowly away from 32-bit stuff. What does that mean for the embedded space? It's going to be a very long time, but it's something to keep in mind. What if NVIDIA goes, forget 32-bit everything? This is stupid. We're going to stop playing around with 32-bit. And, ARM says, okay, boss. Then what?
Then you have Microchip licking their chops.
Right.
Saying, go.
Then Microchip says, we still have 8-bit microcontrollers. We'll give you 4 for your 32 bits. There's also the same thing that we saw when Intel bought Wind River, right? Okay, well, you can say whatever you want, but it really doesn't matter because you're still working for the competition.
There is not one example that I could think of where the stay the course actually stayed the course. Not one.
Which, like we just said, that's, in theory, this is a really big opportunity for RISC-V. And I did see that Sci-Fi made a joint announcement with Intel not too long ago. If it were me, I would be on the phone seriously if I were at one of these RISC-V companies trying to make some big announcements with those companies, because NVIDIA is duking it out with these guys head to head, not just in the data center, but in some of those high-end gateway class applications that we were talking about before too.
The insiders are joined by Intel's Sailesh Kottapalli, Senior Architecture Fellow, and Mandy Mock, VP and GM of Product Engineering Systems, to dig deeper into Moore's Law.
So where are we today with Moore's Law, Dennard scaling, and what are the implications that has on price per watt, performance per watt, size per watt of processors moving forward?
Yeah, in general, there is a lot of chatter about, the Moore's Law ending and things like that. And generally, if you really look at the actual proof, that is not the case. I think in general, from time to time, some or other technology foundry vendor runs into some problem and that slows it for that particular vendor and so on. But in general, if you look across the broader industry, the progression has been fairly steady. Now, the attributes have changed in each generation. The kinds of technical attributes that become available with a technology node change. And then you both have to co-optimize for it in the design as well as architect for those attributes. One thing that is clear is that what we used to get as voltage scaling in every technology node is no longer a knob that is available. There are other knobs that industry is innovating on, but the voltage scaling knob is not scaling at the level that people are used to, and that gets into the entire discussion about what is the level of transistor scaling you get, and what is the power scaling you get, and then the discussions around Dennard scaling and so on, right? So essentially, we get more transistors than the amount of power reductions we get in every technology node, and what that has brought is really for people to co-design better to the attributes of the process to get more power efficiency. And then in actually architecture, where you use those transistors to figure out how to actually reduce the amount of computational work you do to achieve the same particular usage or work or service. And when you do that, because you're doing less work to get to that, you actually make that up in terms of total power consumed to get that work done. So what it will require going forward, and in general, Intel has been clear on this, is every product is underpinned by 6 technology pillars. Process and packaging are one of those, but it needs to be coupled with the compute architecture, innovations in that, the memory architecture, interconnect, what we do in the actual software that allows you to optimally use all the capabilities that have been built into the silicon, and then the technologies that actually make sure that the infrastructure is secure, right? So all of the innovations in that actually help us deliver the value progression that we see from one generation to next, and the technology progression, specifically the process, is an important one, but not the only one.
So to be fair, I want to make sure that we're all talking about the same thing. The literal definition of Moore's law had to do with transistors, and I hear people talking about it in so many different contexts today with respect to power and performance and all of the other things. Are you saying that I think the original definition was that the number of transistors would double every 18 months? Is that right? Is that really what it was? And
that's absolutely right. And that's what I'm saying. If you go by that metric, I think the progression has been fairly steady. Now, the attributes that come with it, whether it's power or how many levels of metal you get and other kinds of things, yes, they have been changing. And in some cases, there is a clear trend of change, right? But yes, I think as that 2x scaling in transistors, that that through different mechanisms has been generally holding, whether it's 2 or 2.5 in some generations, or back to 2, and so on. But that progression is not something that I see going away.
But is that even significant? Since
Right.
we can do so many other things with the available transistors that we have now.
That's the point I like to stress upon. I think in general, the thing I find fascinating is that people who actually build specialized architectures or application-specific architectures talk about Moore's law going away. But when you actually go look at the designs that actually crave for the latest technology node availability, and the ones that land on it, you would actually see that those are the ones that actually land on it the earliest. So, there is a particular benefit you get out of the transistor scaling and everything that comes with the progression of the technology node. But there is innovation outside. So there is the progression that happens in architecture outside of that too. And when both are coupled, you get a bigger jump.
Right. So like what Rich was saying, I was kind of chuckling to myself. I'm like, well, that's great. We're doubling the number of transistors every year. Who cares? Because really the people using these devices, they want, what's important to them is the power, the performance, all of these other things. So now, and I just, again, want to be clear, when you do double at 7, 5, and maybe on into 3, what are you getting? Obviously the returns aren't as much. You talked about the voltage scaling and the amount of leakage that's happening down at those really, really almost atomic level processes. What are you getting by moving, maybe from 16 to 7 and from 7 to 5 and so on and so forth?
Yeah, I think what you're able to do is you're able to do more architecture innovations. And let me just give some simple examples, right? With AI, what we've identified is that the progression is driven by how people can use lower precision computation, right?
Mm-hmm.
So now what we're able to do is actually provision more of that lower precision computation along with everything else that you need to put in your product, right? And now you would exercise that when you are doing that AI computation, and you try to manage your power that is applied to the rest of the system. But when you're not using that, you turn it off, right? So there are architecture innovations that those additional transistors enable that help you actually now drive performance improvements through that. Right? It could be even as simple as we add new instructions. It could be vector instructions and other kinds of extensions that allow you to process that much more efficiently compared to what we were doing in the past. And those are dedicated transistors.
Mm-hmm. Nevertheless, though, I mean, Intel has been moving, like almost everybody else, into this world of heterogeneity, right? You acquired Altera a decade ago now, and also you've had integrated graphics capabilities. I think it's the world's worst kept secret that you've been working on a GPU. How do you think that those different architectural types are going to play into devices moving forward? Are you still going to be plugging ahead with lower and lower geometries and a CPU centric architecture primarily, or do you see more of a play with these heterogeneous systems that are able to do more with different types of compute?
When it comes to actually Moore's law, it's not as if general purpose is the only one that needs Moore's law to make a progression and the rest of them don't. All of them actually need Moore's law because they can benefit from that, right? And I don't differentiate that one needs Moore's law more than other. And essentially all of these architectures and products actually benefit from Moore's law equally.
What it seems to come down to is application focused and very specialized depending on that application. And in a lot of avenues, it's really more about the software than the hardware that it's running on. And are you reaching out into these various applications to make sure that the hardware is tuned to the software, which is actually the opposite of what we've always done, to make the software tuned to the hardware?
That's why we think about the architecture and software as two independent pillars which need to be co-optimized. So we see that with the products that we have, with the right software optimization, the level of performance that can be had is in several cases multiple fold, and an order of magnitude is not surprising in a lot of cases, right? So that's one thing about how do you use all the capabilities that are already provisioned in the hardware well, right? The second piece is how do we find inspiration for how do we make our products better? And actually that comes from, as you really look at what is being done in the actual service and the solution and software, you actually identify where the bottlenecks are and what is actually gets in the way of maybe improving the performance by 2x and so on. And we identify architecture solutions where we can actually use potentially the transistors that are available in a next generation technology node to speed up that and actually then deliver higher performance based on where software is. So we actually optimize the software on our existing hardware, and then we use the software to understand where our next generation hardware needs to be targeted. So it goes both ways.
We spent a lot of time focusing on technologies that are currently or trends that are currently impacting high performance applications. But are we going to see all of these different both architectures and implementation strategies making their way into some of these high-end embedded applications anytime soon?
Yeah, actually, that's very much happening today. And I want to talk about it from two perspectives. So one is we We continue to leverage the advancements that are made by our peers in the client compute and server arenas to deliver embedded solutions or IoT solutions that go further up in the performance range. And the second is we're also investing heavily in bringing IoT-specific technologies to market. So for example, in our most recent product launch, Elkhart Lake, we have capabilities like functional safety, real-time capabilities, out-of-band management solutions that are very specific to the IoT market and really make it easier to implement those solutions. As we see 5G deploy, we're expecting those sorts of solutions to become more and more critical for people to be able to take advantage of the data that's out there at the edge, which we all know is just exploding. And so our goal is to continue to invest in IoT-specific capabilities that will enable our customers to bring those solutions to market faster. I think the holistic view of the whole system is really important. That we want to really help customers to think about their full workloads, and not just the parts that are sexy in the industry right now, like AI or machine learning, but thinking about how you integrate those capabilities to deliver new insights into your existing environment, and that you get the flexibility to not only combine your existing workloads with those new capabilities, but also kind of future-proof yourself against what's going to come in the future. That's where having these more general purpose solutions that you get with like a CPU combined with accelerators or GPUs really comes into advantage.
Moving forward, looking out on the horizon, how much more runway do we have in silicon? Are we, going to ride this pony until it dies, 3 nanometers and beyond, or are you already looking into alternative materials?
This is my third decade in the semiconductor industry, and we've always been 5 to 6 years away from the end.
Right.
And I'm still waiting for that. People talk about post 3 nanometer, and I don't see that ending. But just from a purely taking a step back and talking from architecture, I think as we look at the entire system, how we bring compute, memory, interconnect together, and what is the improvements that can be made in each of them in isolation and in concert of each other. We see that there is a fair amount of silicon improvement that can be done for foreseeable future.
In this week's Tech Market Madness, Perry Cohen tries to make sense of the edge with Matt Trifiro of Vapor.io and Jacob Smith of Equinix, who co-chaired the LF Edge's 2021 State of the Edge report.
More than 10 years after the IoT became a thing itself, a big question many people still ask is, what is the edge? This question is a big reason that Matt Trifiro, the Chief Marketing Officer at Vapor.io, and Jacob Smith, the Vice President of Bare Metal Marketing and Strategy at Equinix, both co-chaired the LF Edge State of the Edge report, an annual research that takes a deep dive into the edge computing landscape to help define a shared technical vocabulary, define market sizes, and drive enabling technologies for the next generation of IoT. So, what's the answer, Matt?
So the joke that Jacob and I had when we started this is you ask 80 people to define edge, you get 110 answers. And I actually did that. I actually went and asked a bunch of people, and I got some really great answers, like the edge is the wall of my data center, the edge is the cell tower, the edge is the embedded device in the camera. My favorite is the edge is the bumper of my car. And the reality is, and I think this in some ways was some of the flaws in the early thinking around edges, there is no one edge. There's actually lots of edges. And the important thing is to figure out which one you're talking about when you're talking about it. And
come on, give it to us straight.
In the 2018 report, we put a stake in the ground. And we said, look, the edge that everybody cares about is the edge of the last mile network. There's two sides to it. There's an infrastructure side and a device side.
So by that definition, the real essence of edge computing can be summarized as moving the workloads closer to the data. Of course, that begets more questions, like how close and under what conditions. The answers to these are almost universal use cases and industry specific. Again, Trifiro.
It might be ideal in some ways to run an edge workload on an embedded device, literally, on the camera or the car, but it might be too expensive because the cost of cameras, the bill of materials is measured in fractions of a penny. So you have all these different trade-offs, and it's a complex world, but so is the entire internet.
His LF Edge co-chair Smith continues.
And I think that there's a little bit more need for definition and clarity from a industry standpoint, like the people who are investing and building and collaborating. Like, we all need to say the same words, but customers, and I think we saw this in the report this year, are just like, give me the value.
Indeed, the pandemic did have an impact that was felt in the report, but not in the way you might think. 2021 State of the Edge research shows that 37% of the global infrastructure edge footprint will be dedicated to mobile and residential consumer use cases by 2028, which is down from 45.1% in the 2020 incarnation of the study. Where could that additional 8% be going? Well, to supporting applications in vertical markets like healthcare, manufacturing, and smart cities. This reallocation occurred, at least in part, because manufacturers realized they could no longer wait 10 years to implement their digital transformation and edge automation strategies. After enduring productivity and efficiency losses through the pandemic shutdowns, OEMs in these industries realized that those 10-year roadmaps had to shrink dramatically.
Every organization that moves something, builds something, ships something, produces something, operates on something, had a 10-year automation plan, and that became a 3-year automation plan. And that's really true. I mean, the board of directors of these companies got together and said, look, we cannot be in this situation again. We have to figure out how to drive more automation. And that has had a pretty significant spillover effect into edge computing, which is a pretty significant component and all that. So COVID has definitely benefited the industry in terms of accelerating the spending and the level of interest in the domain.
Accelerating those deployments translates into capital expenditures of up to $800 billion on edge computing facilities and IT equipment through the year 2028. That's a whole lot of server racks, and, maybe even more important, a whole lot of embedded hardware to serve the varied use cases mentioned previously. But there's a rub. Embedded technology doesn't really scale well at this magnitude because the different requirements of those different use cases. And a scattershot investment approaching $1 trillion doesn't seem like the most efficient way for edge computing to solidify itself as a long-term extension of the internet. It sounds more like the tons of ancient cable lines from long-lost providers and obsolete security systems that were installed over the past 4 decades and are now all but defunct. How can the ubiquitous edge compute install avoid similar to fate? How can the ubiquitous edge compute install avoid a similar fate? Smith has an idea.
The question mark right now is how will we kind of operationalize all of the hardware, which is changing quickly, and it's super expensive and hard to get it in and out of places. And that's not really something we can borrow straight from the cloud, because the cloud is like lots of the same thing in a few places, and the edge is like lots of different things in lots of places. And so the logistics, supply chain, we're just at the beginning of, I think, figuring that out. That's probably why you see so much investment from hyperscalers and OEMs kind of like pushing models out to the edge. We'll just see if the use cases thrive with them. Is that the critical infrastructure has to be at some point shared. And it's hard to build, many distinct edge everythings. And so you kind of find these common denominators on the physical side from an infrastructure standpoint.
Shared infrastructure, huh? Do you see vendors vying for market share in the same vertical applications going halvesies on the rent, power bill, and maintenance for an edge server deployment? Probably not. But there's another kind of shared infrastructure, shared IP. And that is the strength of open source software. Trifiro.
Yeah, and I'll add to that. So yeah, the economics of shared infrastructure are so compelling, let alone like the time to market and the shortness of real estate and fiber in the ground and things like that. But open source software is also a critical component. And so shared software in the economics of that and the acceleration around that is just as important as shared infrastructure. And I think one thing that's different about edge computing that we didn't see in cloud computing 10 years ago is this very, very quick galvanization around open source projects. And in open source projects, you have lots of companies contributing. And I mean, as you know, code wins. And often that's the best way to arrive at a standard stack as opposed to some vendor promulgating, their point of view.
I think the key one that normalizes this is very similar to the way we saw cloud kind of normalize IT, is that the software, e.g. programmability of it, is very important. I mean, that's kind of like a requirement for modern organizations, but think about putting lots of stuff in lots of places and securing it and making it do stuff. It's an automation first world. So that aspect, I think we're all benefiting from, sort of call it the innovation coming out of cloud and cloud native for making stuff consumable. The stuff, I think you're totally right, will remain super diverse and use case driven. And we kind of highlighted that, especially in the hardware focused area, where silicon is becoming a differentiator and there's all kinds of different stuff. There's certainly approaches that are like magic boxes at the edge, but that's kind of the continuation of that same idea, is that it's more of an as a service consumption, but the people building it are putting a lot of specialized technology in it.
But while we're on the topic of open source and hardware, what about open source hardware? Open hardware platforms like Raspberry Pi place schematics and board design files in the public domain to provide students and hobbyists with great access and insight into technology. The ARM-based Broadcom SoC at the heart of the Raspberry Pi isn't open at all. But the move toward openness eventually resulted in technologies like the Open RISC-V instruction set architecture that has yielded truly open source IP cores and SoCs and more open elements of the ARM licensing ecosystem. And these developments haven't been limited to embedded processors and boards. They're also being realized in system-level projects that could benefit edge computing environments, such as Open19. Trifiro.
Yeah, and I'll put a fine point on the Open19 one, which I think is really interesting. So for those listeners who aren't familiar with Open19, it's a standard built around the 19-inch rack. And essentially, it was pioneered by LinkedIn, but now it's an open source project. And it is basically a spec for a chassis that a drawer essentially slides into that mounts in a standard 19-inch box. And that means that anybody, literally me, a marketing person, or a guy or a gal that normally climbs a cell tower, can swap out a $10,000, $50,000 piece of equipment by sliding it in and out of a rack. And that's really important at the edge because you don't have personnel on site all the time.
You want to hear my analogy, Matt? It's the Nespresso capsule, and you gotta have an espresso machine.
Smith continues.
I like it. Exactly.
So that's that operational part, which I think we saw some, if you look at like towers, like Matt mentioned, which that's one aspect of edge computing, but towers have this shared infrastructure standpoint where there's like there's a way of doing that business, and I think we're trying to figure out how we take hardware, computers, technology, which is really what you want to consume, along with a network, and put it in more places. So there's a lot of, I think, open source innovation that will drive that.
To answer those earlier questions of how close this open source technology can be deployed and under what conditions, Trifiro and Smith outline more than 20 vertical markets in the 2021 State of the Edge report, projected the growth of those use cases, forecasted the demand that the growth would place on edge computing infrastructure, and then defined the subsequent investment dollars needed to support that infrastructure. What does that mean for your tech organization? Smith explains.
From an investment standpoint, Perry, I'd say that's all, kind of tired thing. Every business is becoming a software business. But that's going to be like key no matter if you're in mobility or banking or media or whatever else. And that extends to the edge, I think, very naturally. The question that I think is open, and the report kind of teases some of this out, but I think we'll see more, like you said, post-COVID, is how much differentiation, which companies invest in differentiation and which companies sort of just move on reinventing experiences, like, Uberize their sector, right? So, taxis were not great. Uber made them like way better, mainly with software and APIs and other things that they created. But like, will that serve mobility? Mobility might need like a little bit deeper down technology. And that is a question. I think how many companies will be able to invest at the level of sort of fully integrating their technology and then getting it out there at the places it needs to be.
Obviously, that's one of the biggest advantages of open source. The community comes together to develop most of the underlying enabling infrastructure so that companies can invest in differentiating solutions that will reinvent their market. Or, in the case of edge computing, all of the markets. For more information, you can download the LF Edge 2021 State of the Edge report for free from lfedge.org. Thanks for listening to this edition of Embedded Insiders. For daily industry news, videos, and podcasts, visit our website, embeddedcomputing.com.